In the 1960s, the world watched with awe as the development of new materials enabled man to first venture into space and then set foot on the moon.
Tranquility Base here. The Eagle has landed.
50 years on, the discovery of new smart materials is opening up a whole new world of possibilities. Whether it's temperature, light, pressure, or any other number of stimuli, what makes a material smart is that it responds to changes in the environment. And that means smart materials are going to make the world a lot more interactive. Coming up, you'll find out why QTC, or Quantum Tunneling Composite, is set to revolutionize gaming and computer interfaces. You'll find out why NASA thinks shape memory alloys will change the future of air travel. Discover how printed lights will completely alter car and building design, and you'll see how thermochromatic pigments are keeping counterfeiters at bay. Now, if you're a game-playing petrolhead and are rather impressed by things like the latest edition of Pro Street, then you'd better be ready to sit back and strap in. One smart material is about to turn gaming and human-computer interactivity into a three-dimensional experience. It might not have Pro Street's hard rock soundtrack or fast-paced motion graphics, but from a gaming perspective, this lump of QTC, or Quantum Tunneling Composite, is potentially a lot more exciting. First discovered by chance in 1994, what makes it special is that the harder you press it, the better it conducts electricity.
The curiosity of QTC is that it has this huge range of conduction. It can turn from a conductor into an insulator. If I put an insulator on this torch, which has been modified so that we can bring the contacts out, it's not surprising, this being an insulator, that I can't get the torch to work. If I put QTC on here now, it doesn't work until I press it. The QTC is going across that whole range of conduction, over 1 trillion ohms of range. All I can show you is the last few ohms of its range here, but the rest of the range is there.
NASA was among the first organizations to make use of QTC's properties, creating a series of soft switches that enabled astronauts to control helmet fans and other equipment whilst wearing bulky gloves. The same technology is used to control MP3 players and iPods in ski jackets. But recent developments have opened up a whole new range of applications.
We realized that we could turn it from a solid into a powder, and then later on into a coating. It's allowed us to extend the human touch capability, and it's this that's given us such remarkable effects. We can now put touch sensitivity into practically anything. Of late, this has turned out to be touchscreens.
It was a sunny day and the children were going to the park. It was a sunny day and the children were going to the park.
The simplest touchscreens use the same technology you'll find in a Nintendo DS. Two conductive plates are held apart by a layer of spacer dots. Pressing the screen parts the dots, touching the conductive plates together. The system means it's possible to sense simple two-dimensional movements from a finger or stylus. But pressing softer or harder doesn't make any difference. Replacing the spacer dots with a layer of pressure-sensitive QTC adds an extra dimension of interactivity.
Now this is basically got carbon electrodes both sides, silver tracks to both sides of that. Sandwiched in between that you can't really see is actually an area of QTC that is the same size as that carbon area. So what you've got there is, if there was no QTC in there and you had a layer of spacer dots between those two layers holding that very, very minutely apart, you would get a standard trackpad that would sense whereabouts you were as you touched it, and it would be transferred to your software or your screen. With QTC in there, you not only get the position of your finger, but you would then get true pressure sensitivity as you push as well. We have a little demonstration here that shows you a 3D representation of moving around the trackpad. So you'll see as I move around the extremities of the trackpad, it follows my finger on the screen, and the height of the shape is the pressure that I am applying as I move around. So you can see I can, with a definite push like that, I'm getting varied response.
It's still new technology, but adding the dimension of pressure is likely to open up all sorts of new interactive possibilities.
You can imagine someone developing technology where the harder you push, that makes something happen on a screen that you couldn't normally do with a two-dimensional mouse. For instance, if you had a file system, i.e., the Windows Explorer or the Finder on a Mac, just actually finding files in a simple form could be expanded to include, if you were trying to delve down into a directory structure of folders, you could be moving around and you could click on a folder, and you would, if you pushed harder, you would go down into that folder and into that folder. The harder you pushed, you could go down the directory, and you suddenly got a 3D space for finding files, that kind of thing.
Every single bit of QTC is made in this laboratory, and just in case you're thinking of copying the idea, it's a closely guarded secret.
As you can see, we've got plenty of people working on our testing, but in this lab here, this is where we make QTC. This is the only place in the world where we make QTC. And in fact, because it is, I can't show you in there.
But what's got the screen manufacturers buzzing is that the scientists working in this lab have recently had something of a breakthrough.
It always in the past has been opaque. You could never see through a QTC sensor. However, in the last few months, we've now made a clear QTC. It still operates exactly as the other QTCs. You can use it to sense touch, but you can see through it. It's got a complete clarity, which means that you can put it on top of screens that have a video content and control the screen.
The discovery has led to the creation of clear QTC touchpads like this. It also means that the touch-sensitive part of the screen can be placed at the front, making it more sensitive.
You can actually see as I press the corner of the screen, I'm getting a response. But you can see that there's no detrimental effect. With the fact that there's QTC in this sensor, you can see through it. It's not affecting, the optical nature of that screen. Red looks red, black looks black. We are pretty transparent with that. But the technology is the same. You can see.
But the main way QTC is set to revolutionize gaming and other interactivity comes when you increase the number of conductive points.
This that we have here, this is the opaque QTC in a matrix arrangement. Our sensor here is a 16 by 16 grid, giving us 256 discrete sensing points. So we can, at any point where these silver tracks cross, we have a sensing area. Basically, you've got circles appearing where my fingers are touching, and the harder I press, the larger the circles get, and you can see that it is spotting that I have got two fingers there, and that they are individually moving discrete points, whereas you can detect gestures and swipes and twirls and that kind of thing. So basically the data comes in, and then the client will interpret that data to do particular things in their own software. So you can see there that as I move around, it follows me and keeps the points, but I'm getting true pressure sensitivity on each one of these points.
By the time you watch this clip, the clear QTC version of this sensor will already be a reality, and that's got the games industry talking.
The big players in gaming are always looking for the next big thing to sell their console over their competitors, and the big thing there is the user interaction. If you can do something on a console when you're playing a game that you can't do on another console, then obviously that is a big selling point, that kind of thing. And if you can interact with pressure to make something happen on a screen that you couldn't make happen without pressure sensitivity, then that is another big selling point.
You at last 2 seconds against the Dark Lord.
The only real issue is, when it comes to certain games, how interactive do you really want them to be? They might look a little odd, but these aircraft are some of the latest ideas being trialled by NASA. Among the concepts are wings and aeroplanes that change shape when they're in the air. It makes them faster and more fuel efficient, bringing potentially huge benefits to the airlines of the future. But the idea is only possible because of a remarkable range of smart materials. Like NASA's concept aircraft, this wire is made from a nickel-titanium shape memory alloy, or SMA. You can bend and twist it like a piece of steel wire. But when you use electrical current or heat to raise it above its threshold temperature, it enters what's called a super-elastic state and remembers what shape it used to be. By making SMAs with different threshold temperatures, designers have been able to make use of their super-elastic powers.
This is a pair of glasses, and the parts of the frame have been made from something called super-elastic wire, which you can see we can bend the glasses every which way and they just spring straight back into shape. And that's so that your glasses can be sat on, dropped, and in theory they won't break.
But cool the glasses down below their threshold temperature and they don't spontaneously spring back to their original shape.
Differently. So we've taken one arm of the glasses and we've put it into solid carbon dioxide, which is very cold. And you can see now that the bend on the frame is permanent. And if we just let that warm up a little bit, it goes springy again.
But it's not just shape retention that makes memory alloys useful. When they reach their threshold temperature, some shape memory alloys also shrink by up to 5%, exerting a significant pulling force, especially when they're coiled into a spring-like shape. Called muscle or smart wires, these SMAs are increasingly being used as low-cost actuators or switches. One project making use of this property is an automatic gas cooker shut-off knob, developed at the Royal United Hospital in the UK city of Bath.
We were looking at trying to address the needs of people with dementia at home and trying to find ways in which people with dementia at home could be more independent and carry on with doing things that they've been used to doing themselves. So what we set out to do was to design a system that could be fitted to an ordinary cooker that could turn the cooker off if it detected a problem like gas leak or smoke in the kitchen, but not disable the person from carrying on using their cooker afterwards.
Tim and his team began developing a system linking smoke and gas sensors, a control box and sprung-loaded cooker knobs. The idea was that when dangerous levels of smoke or leaking gas were detected, the control box would activate a mechanism inside the knob, releasing the spring and physically turning the knobs to the safe off position.
This part here is the spring that drives the cooker knob when it works, and so when you turn the cooker knob on to get some gas out, you also wind up the spring a bit more, and that's put some energy into the system, which is then stored away in the spring. We have to be careful with these because if they ping out of their housings, they explode really and go all over the place. So we'll put that to one side and leave it there. The way this works is when we turn the cooker knob on, we turn this ratchet here like this, and that winds up the spring here, which we had on earlier, which fits over the top. So the spring's wound up, and all the torque from the spring is applied to this shaft, which goes through the middle here.
With so much tension held in the spring, The design challenge facing Tim was to find an actuator that could be operated by an electrical pulse from the control box, but exert enough force to pull the release lever off the ratchet. The answer came in the form of a muscle or smart wire.
There's a little pair of wires here which run into the Shetland Railway wire inside the cooker knob. If you can see on this one here, there's a wire just in there with little grey terminals on the end. These are then wired through the inside of the cooker, out the back of the cooker, and into a control box which is mounted on the back of the cooker, and into the control box which has a little PIC microcontroller in it, a tiny computer on a chip, a whole computer on a chip really. That's then connected to a smoke sensor and to a gas sensor as well.
Fitting each knob takes around 5 to 10 minutes and has relatively little impact on the look and feel of the cooker, something that's important for people with dementia. Normally the wires are connected to the control box at the back of the cooker, but for this demonstration Tim's using a battery.
Okay, here we go. I'm going to touch the two wires together and we'll trigger the knob to turn off. There we go. So that's a completely automatic cooker turn off, and it's usable again straight away. So I can go straight back to that cooker, which is turned off automatically. Perhaps I'm a person with dementia, I know there's a problem. I can come back on and use the cooker again straight away without having to worry. It still turns off manually if I want to. We haven't changed the way the cooker works. Ooh. We haven't changed the way the cooker works normally at all. It still works exactly like it always worked. We've managed to add an automatic system to increase the safety of the cooker and enable a person with dementia who's forgetful to carry on cooking for themselves independently.
The knobs also performed well during the field testing phase, but in the end the high cost of making and installing them meant the team had to find alternative solutions. But just because they didn't work out in this situation doesn't mean SMAs aren't becoming more important. When man first went into space, the silicon chip was still in its infancy. 40 years on, the average smartphone has 1 million times more processing power than was on the Apollo spacecraft.
It's one small step for man, one giant leap for mankind.
We might laugh at early space technology, but the discovery of organic semiconductors means in 40 years' time, our technology will look antiquated too. And one of the starting points for the research is looking at how these new smart materials can be used to create new forms of lighting.
I have here an OLED. This is an organic light-emitting diode. The word organic can be a little bit misleading. What it really refers to is that it's a carbon-based polymer. Its number of layers printed very, very thinly onto, in this case, a glass substrate. We lay them down very, very thinly, typically at between 5 and 20 nanometer levels, and we end up with a stack typically around 100 nanometers thick. And to give you an idea of 100 nanometers, that's 2,000 times thinner than a human hair. We run a direct current through this, so a DC current, and we can activate the light emissive polymer, and the result is light.
OLEDs make use of a property called electroluminescence. When you electrically charge certain polymers, they emit light. The simplest OLEDs are made up of 3 or 4 different layers, mounted on a glass substrate or base. At the positive electrode, voltage yanks resident electrons out of the inner semiconductor layers, leaving vacancies or holes. At the negative electrode, new electrons are pushed in. When electrodes meet holes, photons are emitted in the form of visible light. The concept of electroluminescence, or EL, isn't new. It was first discovered in the 1950s, but screen-printed EL inks weren't really bright enough to use for lighting, so the uses were limited to posters and other publicity materials. The new polymers give off much more light than the old inks. They can also be tuned to create different colour light, and they're more efficient and environmentally friendly than conventional lighting.
Currently we're talking of something 35 to 40 lumens per watt. That's a measure of efficiency. But eventually we can see a day, in the not too distant future, in the 100 lumens per watt. And to give you some indicator of what that compares to, well, the old-fashioned tungsten bulb would have been something around 8 lumens per watt. So you can see a multiple of factors more efficient. In fact, the Department of Energy in the US said that if, hypothetically, and if it was possible, they were to move to this technology overnight, it would be the equivalent energy saving as closing down 250 power stations.
Because the OLED's layers are extremely thin, the slightest speck of dust would be enough to cause a noticeable imperfection in the light. So they're manufactured in a clean room. Advances in manufacturing techniques have also helped make OLEDs a reality.
This machine is an evaporating tool. It evaporates different materials down onto pieces of glass or plastic. The particular sources in this machine, we currently have 3 of them. The source behind here is for silver, the source behind here is for gold, and behind here is a transparent conductor known as indium tin oxide. The way this works is, first of all, we put a substrate, put the glass in here on a hanger, then it goes in and then it pumps down under vacuum, and then after it's pumped down, it moves the piece of glass backwards and forwards underneath the sources, and the sources are illuminated with a very sort of strong electron beam, and this then fires the silver or gold or whatever onto the piece of glass. By doing this at particular currents and particular speeds, we can control the thicknesses of those layers very accurately. Yeah. So here we've got an example of a piece of glass coated with a couple of pieces of metal. So on here I think it's titanium and gold.
And evaporation is just one of a number of techniques being tried by Richard and his team as they bid to find new ways of manufacturing OLEDs cost effectively.
We use evaporation, spin coating, which is very similar to a potter's wheel type application, and also split blade coating. So we coat in something that's akin to the screening process. So there's a number of different ways to do this, and we work with all 3 different ways, and we're looking at efficiencies and repeatability. When you're trying to do something repeatably at very, very thin layers, it's actually quite difficult. And when you're trying to do it at nano levels, to try and repeatably print something, say 8 inches across, with something that's just a few nanometers thick, gets very, very difficult indeed. So all the focus of the research is how do we improve that? How do we get a more efficient stack, but at the same time making it easier to manufacture?
Installed at a cost of £5.5 million, this machine is a vital part of the development programme. Right now it's being commissioned and tested, but once it's working, it'll be possible to load sheets of glass at one end and take out finished OLED tiles at the other. It might have cost millions of pounds, but this machine is just a research and development stepping stone. And in order to bring manufacturing and production costs down, the eventual aim is to use a plastic backing rather than glass.
When we move to a plastic background, it means that we can go for a roll-to-roll system. Instead of doing individual sheets like this on a one-on-one basis, put them on a large machine, you can print them in large quantities. That means the price will drop. So for consumers, that's a good thing. But secondly, you're basing your materials on a plastic substrate. So that means it's lighter and more flexible. So you can imagine for an automotive use as a dashboard, save a lot of energy and you save a lot of weight in the car, which ultimately is petrol consumption. So it has several advantages. Plus, if this was glass as it is, if I drop this, it will break. With a plastic one, it's much more robust.
Elements of OLED technology are already used in screens for mobile phones and some TVs. For the moment, the cost of OLED lights means their use is restricted to demonstrations and high-end architecture and design. But as costs come down, their use in both screens and lights will become more and more widespread, changing the face of building, car and lighting design forever.
So we have the potential to make flexible lighting panels. So you imagine a piece of plastic we can roll up or even scrunch up eventually. Then we have something that's very, very exciting for artists and architects, people like that. And they tend to get very excited about where can we put light. So already car manufacturers, for example, are thinking, well, if we can bend light and we can turn it into a different form, then we can have something on the back of a car which follows the contours of the car. You're saving space, you're saving weight, and you're saving cost. And also you liberate the designers to do what they like.
For any food retailer, making sure that products stay at the right temperature all the way along the supply chain isn't just vital, it's a legal requirement. And one of the most cost-effective ways of ensuring this happens is to make use of smart materials. Look carefully in some of the chiller cabinets next time you're in the supermarket, and you might well see labels like these. They tell staff that the refrigerators are working correctly. But if the temperature moves above 5 degrees, the OK symbol will disappear. That's because it's made from a thin layer of liquid crystal, a thermochromic material that changes colour at different temperatures.
What's actually happening is that they're going from a liquid state to a crystalline state. They're never completely liquid and they're never completely crystalline, hence they're liquid crystals. But what's happening is that as they're warming up, the structure is organizing itself. And when it organizes itself into a pattern, and that pattern then absorbs some part of the white light and reflects some part of the white light, so that you see it as green.
One of the reasons the chiller labels have become popular with supermarkets is that because they can be screen printed, they're cheap to make. The technology is the same as is used to print t-shirts or make pictures. The black ink being applied here helps the liquid crystal symbol show up as it changes colour. It's the last of 4 layers that make up each sensor.
With liquid crystal, we generally build it up from the back. So the front of the piece is actually there, protected by the paper, and we're building it up from the front backwards. So the first thing we print down is the colour, and in this case we're printing a black. Following that, when it's been through the machine and dried, we then put it through a second time for the second colour. In this case, it's a white. So the white now is going and infilling around the black. We then come to the liquid crystal. That's the next thing that's going down, and in this case we've prepared a window, clear window, for that liquid crystal. So we are printing down, we're laying down the liquid crystal from behind again, so it's going to be red from the front, and it's the symbol OK. But liquid crystal is not really visible until it's got a black backing on it. So the next thing, when this is dried through the machine, we have to put a black backing on. So it then goes through the printing equipment once more, and we lay the final black on the back. That means that the liquid crystal isn't visible until it activates. And it activates, in this case, the formulation has been made to activate at 5 degrees.
Different types of liquid crystals change colour at different temperatures. In this case, the transformation takes place at around 50 degrees centigrade. Unlike the chiller label, as they transform states, the liquid crystals printed onto this sheet pass through the entire colour spectrum. The areas at the upper limit of the threshold temperature are blue, and as they cool back down, they turn green, yellow, orange, and finally red. By combining different types of liquid crystal, research chemist Vicky Mealing is able to fine-tune both the point at which the colour transformation begins and the range it covers. After mixing each batch, she tests a small sample using a temperature-controlled Lincoln plate.
Okay, so this is actual neat liquid crystal. We're going to watch it go through its temperature phase. It will go through a red, green and blue colour change for us. I'm hoping it will start at red about 10 degrees. It's just started now, and that's at 10.7. Okay, so I'm going to carry on heating it up now.
New formulations mean it's possible to make liquid crystals that change colour at any temperature between -20 and +80 degrees centigrade. And being able to tune liquid crystals accurately means it's possible to create thermometers.
In the lab, we've formulated, say, 6 different liquid crystal temperatures. So we've created an ink, and there's 6 inks. So we build up, effectively, a thermometer. And in this case here, each one of these bands is a liquid crystal formulation. It's like laying down a separate colour, but it's liquid crystal. So we now have that is one single thermometer, and that would be then stuck onto something. It could be stuck directly onto a wall in the room, or usually we put it onto a backing card with some instructions about what we're trying to take the temperature of.
Back in the lab, Vicky might have got the right temperature profiles, but in this state, the liquid crystal isn't stable enough to be screen printed.
Here we go again, more gelatin.
By blending her samples with gelatine, she creates a protective wall around the liquid crystal droplets, a process called microencapsulation.
And this is one of our liquid crystals. Okay, so I'm just about to microencapsulate this now. Basically what you're doing is, within the gelatin, you are creating small droplets of liquid crystal, which is what the blender's doing. And later on what will happen is that the gelatin will form a kind of protective wall around the liquid crystal droplets, which protects it when it's then made into an ink.
The thermochromic properties of liquid crystal were first developed about 50 years ago. But these days, it's not the only thermochromic material available.
We also have our chameleon inks. Now, chameleon inks are more of a binary. They don't go through a complete colour change of the spectrum. These are going from one colour to another colour. So on this sheet, we've printed a red chameleon ink. And if I put a cold source onto it, that's the effect.
Rather than liquid crystals, chameleon inks use a combination of fatty acids and colour formers. These enable a colour to be revealed at a specific temperature as the ink cools, or to become transparent as the ink warms up. The inks can also be made to change from one colour to another by adding an additional permanent colour to the mix. But both chameleon inks and liquid crystals are manufactured in the same way.
So we microencapsulated the thermochromic compounds, we then created them into an ink, we then printed the ink down in silkscreen process here. So what I've done is I've actually made cold certain parts of this, and in making that cold, the fats have solidified within the tiny microcapsules of 5 to 15 microns, and the colour is created. Once that's warmed up with my hand, then the fats are melting and the trigger switches again into its colourless form.
Unlike liquid crystals, fatty acid-based thermochromic materials can also be turned into pigments. They can then be added to plastics and used to make things like baby feeding spoons that change colour if the food's too hot. The unique properties of chameleon or phase-changing inks are also being used more and more on the high street. Take a closer look and you might find drinks labels that change colour to show the bottle's cold, or takeaway pizza labels that let you know if it's hot. But increasingly, thermochromic inks are being used in less obvious ways.
Brand products from jeans and perfumes and spirits and cigarettes and DVDs and so forth are counterfeited, and one way of telling that it isn't a counterfeit product is to have some part of the packaging or the label which does something when you activate for instance, a thermochromic ink on it. So, for instance, inspectors or the brand owner, so it might be salespeople or the store owners, can actually tell whether those goods are correct or not.
And it's not just thermochromic inks that are combating fraud. Inside every mobile phone is an irreversible hydrochromic dot. Something that's well worth remembering if you're trying to get your phone replaced under guarantee, when actually you dropped it down the loo.